My name is Stefan Fließcher. I'm the Assistant Managing Director of TEXTECHNO. And TEXTECHNO is a producer of laboratory testing equipment that you can use for R&D and quality control in your laboratory. And I will present to you our latest testing solutions that we can offer for the composite industry, both starting from fiber to yarn to composites and also to the roving. But before going into details of these testing techniques, and there's going to be quite a few of them, I will first give you an idea about the company, and let's see what it looks like. So TEXTECHNO is not so much known up to now in the field of composite testing, though we've been around for 70 years. This year is our 70th anniversary. And the full name of the company is actually not TEXTECHNO, but it's TEXTECHNO Herbert Stein. And on the right-hand side, you see Herbert as he's sitting there on his desk, starting the company in 1949. And we're most widely known in the field of synthetic fiber and synthetic yarn testing. That's really our core market. However, about 10 years ago, we decided we also want to do a dedicated test for composites, and that's why I'm here today. We also have testing solutions for natural fibers, so cotton testing, which is not today's topic, but I will focus, of course, on the composite material testing. I should also say that where TEXTECHNO is taking care of the laboratory equipment, we also have a subsidiary company in Austria called Lansing Instruments, and they are our specialist for online testing equipment. So if you've got any questions in this direction, it will not be covered in this talk, but we can also talk about that. Here you see the production floor of TEXTECHNO. I was saying we were 100% made in Germany, means that when you get a machine made by TEXTECHNO, we have milled the metal, we have soldered the printed circuit boards on it, and we have also programmed the software. So we have a very deep production depth that we're very proud upon. And I think this makes us a very reliable and flexible partner, and of course with an outstanding product quality. Actually, the guys here usually don't work that fast. It's only when I told them I'm going to Istanbul that they were speeding up so much. We're selling our machines worldwide. Biggest markets are, of course, the biggest textile markets as well: India, China, and the US in the last years. And of course, Turkey has been a constant market for us. We're represented in Turkey through Inter, and Tolga, you can wave your hand, sitting in the front, taking both care of sales and service for us in Turkey. But now, finally, let's start with some of the instrumentation techniques I'd like to show to you today. And the first thing I'd like to talk about is mechanical properties of your reinforcement fibers, because you will certainly agree with me that when you have a composite, really the heart and soul of the composite is the fiber that is doing the reinforcement. And I've brought with me a surprise. And you see the surprise here on the left-hand side. And I can't really show you it with the pointer because it doesn't show up on the screen, but there's actually two packages where the vendor of those packages, these carbon fiber packages, is telling you they should have a breaking stress of about 4.5 gigapascal. And it's twice the same material. It's got the same packaging. It's just package 1 and package 2 of the same material. And then you start measuring the tensile strength, and it's supposed to be 4.5 gigapascal. But it actually, on the left-hand side, these bars, they indicate that for the first package on the left-hand side, you really match the vendor specification. But for the second package, you have a loss of about 10% of the total tensile strength in that package. So for some reason, the quality of that package is not as good as you want it to, indicating that either it would be a good idea to have a quality control of your incoming goods, or as a producer of these packages to actually be in control of why the tensile strength is not what it's supposed to be. So it's supposed to be 4.5 gigapascal, and on the left-hand side I'm showing two testing methods because we're testing equipment maker. And on the left-hand side, this yarn testing in dark gray. That's the traditional testing method that you see on the lower left-hand side, where you take the roving, you impregnate it, and you go to a big tensile testing machine and break it. And of course, that's a cumbersome process because you have to mess around with the epoxy. It's very difficult. And what we are proposing, what you can do with our machines, is to actually perform the test, as you see on the right-hand side, on a single fiber level. And this gives the same results as the big tensile testing machine, but you can do it with a single fiber. And this has many advantages. The test is way faster. You don't have to mess around with the epoxies. It's relatively easy to do. It doesn't rely so much on the skill set of the operator. You need a very low sample amount, And you can even test short fibers. So if you're looking, for instance, into recycling of carbon fiber, this is basically the only way of how to do a proper test of the quality of your fiber. And of course, I should show you how the single fiber testing is done. And it's done with the machine here on the right-hand side, which is called the FIBER-MAT. And it's a dedicated single fiber testing machine, which is suitable for all kinds of fibers, and it's suitable, of course, also for carbon fiber and glass fiber. You also see on the right-hand side, the robot is an automation, so you can even feed 500 fibers and will fully automatically test these fibers. And the nice thing about the machine is that makes this test so easy and applicable is that we use direct clamping. So I have this small video here on the left-hand side. And actually, do you hear me when I'm talking just loud? Do I need the microphone? Oh, okay, I'm walking away. So we've got a fiber here and it's being clamped directly. Whereas in the traditional testing methods, you need these small paper frames, but we use direct clamping, which even makes single fiber testing very simple to do. And integrated in this testing zone is also not only a tensile test, but there's also a measurement of the diameter going on at the same time. So it's actually two measurements combined into the same device. And why is that important? This is because we not only need the tensile strength, the force when the fiber breaks, but really want to give out the value and stress in gigapascals. So we have to normalize the forces that you measure onto the cross-sectional area of each individual fiber. And we're doing this with a so-called vibroscopic method. And that's a method I'd like to explain to you a little bit because it's not so widely known in composites, though it's a standard test for textiles. So textile fibers are always tested with a vibroscopic method. And the test is very simple. It's much faster than any microscopic method. And the way we do it is, imagine you have a guitar at home. We're looking for the resonance frequency of your carbon or your glass fiber under well-known gauge length and under well-known tension. And just as on a guitar, when you increase the tension of your fret on the guitar, the tone goes up. And if you put a finger on your guitar, the gauge length gets shorter and the tone goes up. And by knowing the gauge length and the tension, looking at the resonance frequency, looking at the tone of the single fiber that we're testing here, we know how thick the fiber is. Because just like on a guitar, the thicker strings give you the lower tone, and just the same principle is being used here. So it's a very direct and clever way of how to measure the cross-sectional area of a fiber. In combination, this yields results which look like this. So I've brought with me an example here of 20 carbon fibers that have been tested. It takes about 15 minutes to do the test, and it tells you the modulus of the fiber as well as the ultimate breaking strength in 15 minutes. You see what the FIBER-MAT has recorded here on the left-hand side is a force elongation curve, and you see for these 20 fibers the individual force elongation diagrams. Now we've integrated the diameter measurement on each it's performed on each single fiber, and this translates the force to the right-hand side diagram, where force is now expressed as stress. So it's normalized to the cross-sectional area. And now you see that there's actually a huge variation from fiber to fiber in terms of cross-section. But when you normalize it to the cross-section and express it as stress, you get a very smooth curve where all the fibers line up on top of one another. And it gives you a very fast and direct measure of the modulus, which is of course the most important property of a carbon or glass fiber, being here about 275 gigapascal. I'd like to stay, now this is the second topic of my talk, is fiber matrix adhesion, and I'd like to convince you that also for fiber matrix adhesion, it's actually a good thing to test this with a single fiber level. As you know, when you've got a composite, the fibers can be very good, but it doesn't really help you. Also, the surrounding material, the plastic, can be very good. It doesn't really help you. What you need is to transfer the load from fiber into the matrix and then from the matrix into the next fiber again. And that's, of course, going over the interface. And that's why fiber matrix adhesion, the interfacial bonding, the interfacial quality, is such an important quality measure, a key quality measure for composites. And various test procedures have been implemented to actually assess this. Probably the most widely known is this ILSS testing, where I have the little pictogram here on the lower left-hand side. It's like this 3-point short beam bending stiffness test. However, we think that these macroscopic test methods, like the ILSS test, are actually cumbersome to do because you have to be very skilled. The operator really has to know what you're doing, and you have to be in very tight control of all the processing that you make during the generation of the sample. That's actually a list here of all the properties of the composite that impinge on the results in an ILSS test. So you have to be very sure that all these properties you're in tight control if you really want to learn from the macroscopic testing something about the fiber matrix adhesion. However, the alternative to this macroscopic test method is actually to do a microscopic test method. And the one that we are proposing here is a so-called micromechanical pull-out test, where, as you see on the right-hand side, there's a single fiber embedded into a droplet, and we pull out that single fiber. And you see that the number of parameters making a difference to the result that you receive from your testing machine is now much more reduced. There's a shorter amount of impinging parameters, and the parameters which are now left, besides the fiber matrix adhesion, can be very tightly controlled. Here's actually what a test sample looks like. It's pretty small. It's a droplet of about 3.5 millimeter size. And in this specific example, it's a single carbon fiber sticking out of the epoxy matrix that I've brought with me. Important for the test is it really works with any kind of fiber, both glass, also carbon fiber, even synthetic fibers. And it works also for any kind of matrix. So you can do both thermoset and thermoplastic matrices, and you can even do cement, which has been recently pretty much asked for. And what I have to show you now is how to prepare these samples and how to actually do the pull-out test, because we need to grab the fiber, pull it out, and the idea is, well, the stronger you need more force you need to pull out the fiber, the better is the adhesion between fiber and matrix. And we do this with a so-called FIMA test system, consisting of two devices. On the left-hand side, you see the FIMA bond, which is the device that is dedicated to the manufacturing of these small single-fiber composites. And on the right-hand side, you see the FIBER-MAT, and that's the device that I was already presenting to you earlier in the talk, which is this dedicated tensile testing machine for fibers. So it's reused in the system to also measure fiber matrix adhesion, and in the overall combination, you're not only able with the system to measure fiber matrix adhesion alone, but also the tensile strength and the diameter of your fiber. Now, actually, I could now run very specifically to each of the processing steps, but we do have the system here at our booth B2. So if you really want to run a test, you're very much invited to come over and to see it, and actually you can operate it yourself if you want to, or run you through the system. So I can cut short a little bit on the sample preparation and just give you a general idea over here. There's one thing I'd like to show you inside the FIMA bond. It's the latest feature, and I don't have it here on the booth because the device isn't equipped with that. But so I would like to show it here in the video, is that while embedding this fiber into the droplet, we are now also able to measure the contact angle between the matrix and the fiber up to temperature, at high temperatures, up to 400 degrees. And this is, of course, giving an additional measure of the bonding quality, because now you learn about the contact angle, telling you about the wetting quality of your matrix system. So that's actually the latest feature that we've just presented this year on the JEC for the first time. So that's the overall system. We've generated the sample with a single fiber sticking out in the middle, and usually what we do is we go over to the tensile testing machine, turn the sample upside down, the fiber is pointing downwards, and then we pull on the fiber. And I've got a video here with me which is very telling about how the process really looks like, or what it's supposed to be. You see epoxy matrix droplet pointing downwards, and there's actually, you see how the fiber, a pretty coarse fiber, is embedded inside the matrix. And if I run this video again, you'll see that as we are continuing to pull on that fiber, at some point there where the red arrow goes, there's a crack forming. We have to wait for a second. There's a crack. And now this crack is propagating along the fiber until it eventually reaches the tip, and now the full fiber has been broken loose and slips out. And the really interesting thing is that we are able, with this test system, to identify the force where this initial crack is forming, because that's just the force or the stress where the bonds are really being loosened. And that's the power of this microscopic testing technique of single fiber pull-out testing. Here's what the force displacement curves looks like. I'm not going to go too much into detail at this, but the important thing is that it's a very clean measure of fiber matrix adhesion on its own in terms of local interfacial shear strength, and it's corrected for all the complicated deformations that go on otherwise in such a test. Here, I think I've got 4 examples of different fibers and matrices that we've measured. This is a carbon fiber and polyamide. On the left-hand side, you see an unsized carbon fiber. On the right-hand side, you see how the pull-out curves look like for when the fiber received the proper sizing. You see that it already makes a huge difference in the test, even not looking at the derived quantities. Maybe a few more examples are given here. We've got PEEK embedded in a carbon fiber embedded in PEEK. On the left-hand side, you see that there was a standard carbon fiber and a treated carbon fiber, and it made a huge difference in the local interfacial shear strength that we are assessing. The second example is a glass fiber and polyamide. Then there is a glass fiber and epoxy, and a glass fiber and PP. So actually we haven't come through any combination of fiber and matrix that we weren't able to measure. Here an example coming from a hybrid yarn. That's a study that we've performed together with PHP Fibers. And what they do, they make a stacked yarn. Consisting of a glass fiber core, and on top and below there's PP fibers in this case. And they were asking, well, how much maleic anhydride do you have to put into the spinning process of the PP fibers to improve the adhesion to the glass core once this goes into the big bench press? And you see the local interfacial shear strength as a function of maleic anhydride in the spinning processes, which is added through a master batch. And you see that it's peaking at around 6%. So we help them to optimize their spinning process in terms of adhesional properties for their final composite. And here the last example for FEMA test. This is an example coming out of the wind blade business. For wind blades, the most common system to use, of course, glass fiber and epoxy, but the glass fiber sizing for the epoxy is aging as a function of time. So many people are running ILSS testing as an incoming good control to be sure that the fibers are not too old, essentially. This is an example that we've run together with Alström in Finland, and they were performing a transverse tensile test, TTS, and we did it on 2 samples. This is these 2 rows in the table down there, and the one glass fiber was fresh, and the other one was an aged glass fiber. And you see how in the transverse tensile strength test, the shear strength is dropping from 55 megapascal to 38. And basically we were able to prove the same behavior also with the micromechanical testing. The advantage being of the micromechanical test that the turnover times is about 2 days for this test, whereas it took them a long time to do the macromechanical testing. Actually takes them 2 weeks. So it's a huge speed up in testing time until you know if you can really use these fibers inside your production. So that was it that I wanted to tell about fiber matrix adhesion. Now we are going away from the fibers and looking at fabrics and non-crimp fabrics. And as you know, there's a production trend is to go away from hand layup, but you want to have more automized process, which often include the draping of the fabric. And we have a testing machine that assesses the problems that you see during draping of fabrics. When you deform a fabric, you see, and you push it from your 2D-dimensional shape into some complex shape, you see that waves are forming, waves that you don't want. There are undulation and loop forming of single rovings starting to stick out of the surface, which is cumbersome. And of course, most prominently, there are gaps forming where fiber material is missing, and in your final composite, you will have a void of just pure plastic without the reinforcement. Now we have a machine which allows you to assess the drapability of these fabrics to tell you if a fabric will really nicely adhere to a new shape you want to push it in, or if it's going to give you trouble. And the device is called the drapability tester drape test. What we do here is we hold a sample of about pizza-sized shape, 30 centimeters across, with a ring. And then from underneath, there's a piston moving in, forming it into different drape heights, forming it into a different shape. And while we're doing this deformation of the fabric, we can actually monitor what's going on with 3 different monitoring systems. There's 2 cameras and a laser triangulation. And in this way, at each height of the draping process, we can tell you how many gaps there are, how many undulations are happening, and if there's any waves. And I think I've got a small video showing you, giving you an idea of what the process really looks like. But it doesn't really show it. It actually doesn't do anything anymore. Maybe you have to wait for a second. I walked down and tried to start it here. Oh, that was going. So the movie apparently doesn't want to show, but basically it moves up, and at each drape height it makes a detailed picture, which in the end look like this. And the software automatically goes in and checks for what the fiber orientation is and gives you with a color scheme from green being okay, yellow being difficult, and red being catastrophic, an idea of how much the fiber orientation is varying due to the draping that you're doing. That's what you see on the left-hand side, and on the right-hand side you get an idea of how the gaps are forming, so also the automatic image analysis goes in and qualifies and quantifies how big the gaps are, and in the end you receive a statistical evaluation of these defects that you see. I should also mention for drape test that we've introduced this into an ISO committee, so on a short time scale there will be an ISO standard for this kind of test, for this kind of testing. Short notice here on STEDIMAT4U. We also have, our company is actually pretty much known for automatic tensile testing machines, which usually are applied to yarns. But we've got a STEDIMAT4U, which actually is pretty widely used for glass yarn testing. So we have many customers doing tensile strengths on yarns, glass yarns on this machine. But I have a specific example that I would like to share with you coming from the glass fiber business. You see here that this device is not only measuring the tensile strength of the yarn, it can also do an automatic count test, so checking the linear density of the yarn. It does this fully automatically, and we had a customer coming in, he was complaining that the yarn, the roving he was buying, the glass, actually was out of specification in terms of weight per unit length. And this machine was used now to check 10,000 meters, that's basically a full bobbin of glass fibers, to check the linear density, and it does it on pieces of 5 meters, next 5 meters, next 5 meters, several thousand times. It does it fully automatically, and we see the linear density that it has measured on the left-hand side. And you see in this curve that we're actually starting low, around 2,250 TEX, whereas the vendor specification for that roving was actually around 2,400 TEX. So the customer had the problem that he goes into a weaving process or an NCF process, and then he's starting with thinner yarns, and then you're ending up with gaps in his final product. And here you can automatically check that indeed, in the beginning of the roving, pulling it out from inside out, you have a big problem, and it just slowly gets within the specification of the linear density where it's supposed to be. So 2 messages, watch out, this can happen, right? So these are off-the-shelf yarns, and point 2 is it can also be measured automatically. So now I'm closing in on the final device that I'd like to show you, and this is a new device that we've just 2 years ago presented the first time. It's called the so-called roving test, and that's a system to assess the processing properties of rovings and yarns. Because, you know, the properties of the yarn might be very good on the specification sheet, but then when you put it into a production machine, you might face big problems because you also have to guide all the yarns over the surfaces, and it might create a mess with fluff flying around, with deposit being created on the surfaces, and with even the fibers breaking. And we've devised a machine which actually allows to assess these kind of processing properties of rovings. And it's called Roving Test. It's a modular test system. You see the different test sections that you can arrange the way that you want to here on the picture. And we're starting off on the left-hand side by unwinding a roving. It can be glass fiber or carbon fiber roving. And then we run the yarn through the machine and wind it up on the right-hand side. And at the same time, while going through the machine, we do check different properties of that roving under well-defined testing conditions, because the machine checks what is the tension in the yarn and also adjusts the speeds to the testing conditions that you wish. And what we're able to measure is the number of broken filaments on the yarn as it comes off the bobbin, and how many broken filaments have been added to the various tests. We are also able to measure the coefficient of friction and the amount of fluff being created while doing the friction, because we're collecting all the fibers that come off through a suction system and put them on a scale and weigh them, so you can tell how many milligram of loss you have or you can expect in your production machine while you're running the roving through it. And then we have a pretty big spreading unit here in the middle. This guy. Which is heated spreading bars. And before and after the spreading, we can actually, with a camera system, measure the width of the roving. So we can get an idea of how wide you can actually spread out the roving. And that's also the example I'd like to show you. I'd like to show you a few pictures coming from the second camera. So here's what it looks like when you take the data. So there's actually 3 examples. There's one glass roving on top, a second glass roving, and a carbon fiber roving underneath. The width that you see here is about 12 millimeters, but the length is now about 50 meters. So it's a condensed picture of the roving. And it's after spreading, so we've spread out the glass in this case, and in the top row you see that after spreading the width is pretty regular, so it's a very even width. However, on the second row, there's a different product, and you can see that under the same testing conditions, the width after spreading is much different, right? It doesn't spread out as regular as you wish it to be. So the spreadability of that roving is much worse than the first product. And finally, the carbon example is also interesting. The width is way wider than on glass in this case. And in between, you see there's a gap forming, where after spreading, actually the yarn splits in 2, and then after a while it comes back. And you also see that there's a thin place where the yarn has been not as wide, and that was actually a false twist that has been on the bobbin now coming through the machine. And false twist, of course, hinders the yarn to go to through the spreading process properly. So these are the kind of properties that you're actually able to measure with the roving test. On top of this, also interesting is usually this friction and fluff. And just to give you a rough idea, the yarn runs in. It rubs over a surface, might be a ceramic pin or some guiding element of your machine you can put into the machine, into this tester, and it measures the force before and after under well-known wrap angle, so you can actually have a measure of the coefficient of friction that you see in the upper right-hand plot. And the coefficient of friction has here been measured over a short length, about 2 meters, and you see that it came out to be 0.32, 0.23, roundabout, and you see how it's also varying as a function of length along the roving. So that's an interesting quantity also in combination with the fiber matrix adhesion testing, because in fiber matrix adhesion you want your material to be sticky, but for processing you actually want it to slip nicely through your machine, so it's like it goes together and it's competing properties that you might prefer. Well, that's basically what I wanted to show to you in terms of testing techniques that TEXTECHNO can offer. I hope I was able to convince you that we have very interesting techniques, both covering the range of fibers, fiber matrix adhesion, roving, even for fabric testing. There's certain topics that we have not touched upon, like the online monitoring business, but we can still have a chat at the booth. And I would kindly say thank you for attending the talk. And if you're interested, come over to a booth. We're still there. You can put hands on our machines. Thank you very, very much.